This is an introduction to probability. Before we start talking about probability, let's get familiar with some terminology. When we discuss probability of something, first we need to describe what is our experiment. An experiment is an activity with observable outcomes. That means we need to know what kind of outcomes can we expect and what kind of outcomes we are interested in. For example, we can flip a coin, so we have two possible outcomes, either head or tail. Or we can roll a dice, so we have 6 possible outcomes, either 1, 2, 3, 4, 5, or 6. So those are very popular experiments, flipping a coin or rolling a dice. But we could also observe the lifespan of certain population. Could be lifespan of people, or lifespan of some bacteria, or certain type of animals, etc. Where we are already clear about what is the experiment that we are performing, we could build a sample space. Sample space is a set of all possible outcomes of particular experiment. For example, if we roll a dice, as I mentioned before, the outcomes are 1, 2, 3, 4, 5, 6. So our sample space would be a set composed of 6 numbers. An event is a subset of a sample space. For example, if we still refer to the rolling a dice experiment, one of such event would be obtaining an even number. So this event will consist of numbers 2, 4, and 6. So yes, it is a subset of a sample space. If we think about event that contains only one outcome, so that refers to a one-element subset of a sample space, such an event is called an elementary event. And what is a probability? Probability is really a function. It's a function from the set of events into an interval from 0 to 1 with the endpoints. This function needs to satisfy certain conditions. For example, the value assigned to the event represented by an empty set is 0. The value assigned to the event that is composed of all possible outcomes, that means to the sample space, this value is 1. And probability of the union of two events is the same as sum of probabilities of each event separately, as long as these two events are mutually exclusive. What does this mean, mutually exclusive? That means that the two events do not intersect. So they are separated from each other. For example, if my experiment is to pick a point from these two regions of the plane, inside these two loops, and if the event A is to pick a point from this particular set A, but the event B is to pick a point from the set B, then the probability of taking a point from either A or B is the same as probability of taking a point from A plus probability of taking a point from B. Notice that this wouldn't be true if the A and B would overlap, because in this case, probability works like area. Area of A and B is just area of A plus area of B. But area of A union B in this situation will be less than area of A and area of B because of this overlapping part. So mutually exclusive events are the disjoint ones. And for such events, probability of a sum is sum of probabilities. So as soon as we find a function p that will satisfy these three conditions, such a function will be called probability. As you see, the range of a probability function is between 0 and 1 with the endpoints. So usually it's a fractional number. It will never be over 1. And obviously those numbers could be identified with percentages, so it's basically between 0 and 100%. Often we'll work with sample spaces that are composed of outcomes that will have the same probability of occurring. So such outcomes are called equally likely. If we work with equally likely outcomes, then probability of an event A, which is a subset of a sample space S, is the ratio of the number of outcomes in A over the number of outcomes in the sample space S. The outcomes of A are called favorable outcomes, and the outcomes in the sample space S are called all possible outcomes. Therefore, probability of A is the same as number of favorable outcomes over number of all possible outcomes. The double bar enclosing the set A represents cardinality of set A, which is really number of elements of the set A. So cardinality. For example, cardinality of 1, 2, 3, 4 is 4. 4 elements. Okay, using the terminology that we just talked about, let's practice a bit. Assume a coin is tossed 3 times. Find the sample space for this experiment. Okay, to see the sample space, what we need to do is to list all the possible outcomes. So what may happen when we toss a coin first time? We may get either head or tail. Using the first toss as head, the second one may be head again, or it may be tail. Similarly, if the first toss was tail, the second one could be head or tail. So at this second level, we already listed all possible outcomes after tossing a coin 2 times, but we need to do it 3 times. So one more step. Let's say after the first 2 tosses we had head, head. The third one again, it could add another head or tail. The second possibility, again, we may have head, tail, and head, or head, tail, and tail. And in the following possibility, first tail, head, and then head again, or tail, head, and tail again. Finally, tail, tail, and head, or tail, tail, and tail. So this way we have 1, 2, 3, 4, 5, 6, 7, 8 possible outcomes. That's our sample space. After 3 times tossing a coin, we can end up with this kind of outcomes. Find the favorable outcomes of the event of obtaining exactly 2 heads. So, which outcome has exactly 2 heads? This one not, that one yes, that one yes, that's not, that's yes, no, no, no. Okay, so there's 3 possible outcomes. Let's call this event A. It consists of 3 outcomes: head, head, tail, head, tail, head, and tail, head, head. Finally, find the probability that we get exactly 2 heads in this experiment. Well, probability of obtaining exactly 2 heads, that means of obtaining event A, is the cardinality of A over cardinality of S. Since we have 3 elements in the set A, the cardinality of A is 3, and we have 8 elements in the set S, so the cardinality of S is 8. Therefore, the probability of obtaining exactly 2 heads is 3/8. What are independent events? Independent events are such that the outcome of the first event does not influence the outcome of the second event. For example, if we repeat the same experiment, like tossing a coin, or performing 2 independent events, like tossing a coin or rolling a dice, the outcome of tossing a coin, for example head or tail, doesn't influence the outcome of rolling a dice, and vice versa. So these 2 events are independent. If we work with independent events, then we can say that probability of the intersection of 2 events is the same as the product of probabilities of these 2 events. So this is probability of a new set, which is the intersection, and this is a product of 2 numbers, because remember, probability gives you a number. Okay, let's use this fact. Suppose we select, without looking, 2 marbles from a bag containing 4 red marbles and 10 green marbles. What is the probability of selecting marbles of 2 different colors if we select them with replacement? So imagine we have a bucket of marbles. We pick one, but after recording the outcome, we put this marble back to the bucket and then pick a marble from the bucket again. So the bucket is prepared exactly the same way as before the first picking. Therefore, such two events are really independent. Okay, let's picture out the bucket and our marbles. There's 4 red marbles. We'll draw them. And there's 10 green marbles. Let's draw them. 5 here, 5 there. 10 green marbles. Now, if we want to select 2 different colors, it may be that first we pick red and then green, or we can pick green first and then red. So those are 2 favorable outcomes of picking 2 marbles with replacement. Therefore, the probability of such event, it will be the same as probability of getting red and green and then adding probability of getting green and red. What is the probability of getting red marble first? Well, since we have 4 red marbles out of 14 possible marbles, this probability will be 4 out of 14. And then we have to multiply by probability of getting green marble. But remember, the red was replaced, so we still have 14. Therefore, probability of getting green is 10 out of 14. The same situation will happen if the green is picked first. Green out of everything is like 10 out of 14, and red is 4 out of 14. So we really have 2 times the same probability. The numbers are written in different order, but overall product is the same. If we reduce those numbers, that will be 2 sevenths from the first fraction and 5 sevenths from the second fraction. Therefore, overall, we have 20 49ths. Now, to find out the same probability of getting 2 marbles of different colors without replacement, that means our events are really dependent, because if we pick red, then the remaining number of marbles will change. It will be 13. So the probability of picking the next green will depend on what we picked before. Those are the dependent events. How would we calculate? We can do the same as before, or we could use the following method. We want to pick 1 green and 1 red for sure, because we want to have 2 different colors. So in how many ways we can pick red out of the 4 reds? That's number of combinations. 4 choose 1. And then in how many ways we can pick 1 green? That will be 10 choose 1. So here we calculated all favorable outcomes. And now we need to divide this over all possible outcomes. Altogether, what we need to do, we want to pick 2 marbles out of all 14. So all possible outcomes is 14 choose 2. And now we can calculate how much is that. In the numerator, we have just 4 times 10. And in the denominator, we have 14 factorial over 2 factorial, 12 factorial. So when we reduce 12 factorial with 14 factorial, what's left is 13 and 14. That could be reduced with the 2 and leaving us with 7. Therefore, overall, we have 4 times 10, and in the bottom, 13 times 7. So the numerator is 40, and the denominator is 91. So the probability of picking 2 different color marbles without replacement is 40 out of 91. Notice that this could be calculated in a similar way as the first point. So let's write our possible outcomes: red and then green, or green and then red. Originally, the red marble can be picked with probability 4/14, but then the green one because we already have 13 leftover marbles, the green one will be 10 out of 13 plus, and then again, to pick the green originally, it will be 10 out of 14, but then the red one, it will be 4 out of 13. So overall, we really have the same two fractions. So that will be like 2 times. If we reduce 14 with 10, this will be 7, that will be 5. So the numerator will be actually 2 times 20, and denominator 7 times 13, which is 91. So as you see, we really have 40 over 91. Therefore, the second point can be calculated in two different ways, either like this or like that. Personally, I think that this method is nicer. Let's see the next example. A committee of 4 is chosen from 3 accountants and 5 actuaries. Find the probability that the committee has exactly 2 accountants. Okay, let's picture the situation first. We have 3 accountants, let's say these 3, and 5 actuaries, 5 of those. And what we want to do is to form 4 of them. Among those 4, we may have no accountants, we may have 1 accountant, or 2 or 3 accountants. We need to find the probability that the committee has exactly 2 accountants. So we want to pick 2 out of those green ones out of the accountants. There is 3, we need to choose 2 out of them. And then we want to choose the remaining 2 out of the actuaries. So there's 5 actuaries, we are picking 2 out of them. So that's the number of our favorable outcomes. However, what's the number of all possible outcomes? Altogether, we're choosing 4 out of available 8, 5 and 3. So 8 choose 4 in the bottom. And then we calculate. 3 choose 2 is just 3. 5 choose 2 is 5 factorial over 2 factorial, 3 factorial. In the bottom, we have 8 factorial over 4 factorial, 4 factorial. So if we simplify the 3 with 5, leaving with 4 times 5, and reduce with 2, that will be 10. 10 times 3 is 30. And in the bottom, we have, after reducing the 4 factorial, we'll have 5 times 6 times 7 times 8. And the other 4 factorial is the same as 2 times 3 times 4. 2 times 4 can be reduced with 8, and the 3 with 6, leaving us with 2 instead of 6. So we have 2 times 5, 10 times 7, 70. And finally, if we reduce by 10, we end up just with 3/7. So this probability is really 3/7. Next, let's talk about binomial probability. That will be quite useful in statistics courses. If an experiment consists of n independent trials with probability p of success in a single trial, then the probability of k successes is given by this formula. That's part of binomial formula. We have n choose k, and then the probability of success to the k times probability of failure to n minus k, where q is the probability of failure, 1 minus p. Let's see how this works. A dice is rolled 10 times. So each time we roll a dice, we know that, for example, probability of getting the 6 is 1/6. Now we want to find the probability that we get 6 exactly 3 times. So the probability of success is 1/6. Therefore, probability of failure is 1 minus it, so it's the same as 5/6. To get this result exactly 3 times, we want the number of successes to be 3. So the k is 3. The number of overall trials that we use is 10. We roll the dice 10 times. Therefore, the probability of getting 6 exactly 3 times out of these 10 trials is 10 choose 3 1/6 to the k, which is 3, times probability of failure 5/6 to the 10 minus 3, so it's to the 7. And then we can use calculator. 10 choose 3 is the same as 120. Now in the numerator we really have 5 to the 7, denominator is 6 to the 10. So when you plug it into the calculator, this turned out to be 0.155, just 15.5% chance. Now let's find the probability that we get 6 at least 3 times. Not exactly 3 times, but at least 3 times. That means we will have to find out what is the probability of getting it 3 times and 4 times and 5 times and 6 times. Well, it's a lot easier to calculate the remaining probability of getting it less than 3 times. So it's a lot easier to start with 1, as probability of all possible outcomes is just 1, and subtract the probability of the complementary event. That means probability of getting 6 less than 3 times, which means 0 times, 1 time, or 2 times. So let's mark those probabilities as P0, P1, and P2. Okay, 1 minus P0. If k is 0, we have 10 choose 0. Our probability of success is 1/6, but it is to the 0. No successes. Failure 5/6 to the 10. And then do the same for 10 choose 1. 1/6 to the 1 and 5/6 to the 9. And finally 10 choose 2. 1/6 to the 2 and 5/6 to the 8. This is still less calculation than if we would calculate 3, 4, 5, and 6 separately. So we'll have 1 minus, and in the bracket, this is 1, that's 1, this is 5/6 to the 10s. So it's 5/6 to the 10s, plus, that's 10, and here we have really 5 to the 9s over 6 to the 10s. And the last term, 10 choose 2, you can check that's 45. And here we have 5 to the 8 over 6 to the 10s. Now we need to plug it in to the calculator and figure out how much is that. I've got the result 0.22477. 5 places, that's good enough. So we're about 22% sure that if we roll a dice 10 times, we'll get 6 at least 3 times. And here we have another probability rule. If we calculate probability of a union of 2 events, so for example, if we talk about the sets of points in those 2 loops, the first one is A, the second one is called B, then the probability of a union is probability of A, you can think about area of A, plus probability of B, area of B, but then the common part is counted twice, so we need to subtract probability of the intersection of the 2 events. So probability of a union is probability of one set plus probability of the other set minus the probability of the common part of these 2 sets. Using this rule, let's solve the next problem. What is the probability of drawing an ace or a diamond from a well-shuffled deck of cards? And here we have a deck of cards. So even if we don't play cards, we see what is this deck of cards composed of. We have 4 aces here, and the diamonds are here. Okay, so these are the 2 overlapping sets. Therefore, if I want to calculate the probability of obtaining an ace, let's call it A, or diamond, let's call it D, and or will be union, then this is the same as probability of A plus probability of D minus the probability of intersection, A intersected with D. So what's P of A? We have 4 aces, And the deck of cards has overall 52 cards. There's 4 aces and there's 13 diamonds. Okay, therefore we have 4 aces out of 52 plus 13 diamonds out of overall 52 cards, and then we need to subtract the probability of the intersection, which is just one ace and a diamond. That's the one. Okay, so it's 1 over 52. Overall, we have 17 minus 1 is 16 out of 52. And if we reduce this, let's say divide by 4, we'll end up with 4 13ths. So that's the overall probability of picking an ace or a diamond. Watch the OR connection. If it will be ace and a diamond, that will be just 1 52th. But ace or a diamond is 4 13ths. And 4 13ths really represents about 30-31%. So you had some sample what probability is about. You may learn more about probability when you take any statistics course or discrete math course.